All right, so we left off talking about probability rules. So we're going to kind of look at one which is a little bit different, which is this multiplication rule. Okay. So I kind of glossed over conditional probabilities a little bit earlier, but now we're really going to focus on them because I think it's easier to talk about them when we actually talk about them with probabilities. So my multiplication rule is simply saying that if I want the intersection of two events, I can rewrite that as a conditional probability. So a conditional probability is whatever's on the right-hand side of this line, we're assuming that that has occurred. So I have an outcome and it's in event space A, right? So given that I'm in A, what's the probability that I see B occur? That's how I would read this conditional probability. What's the probability of B given that A has occurred? Now notice I can write that intersection of the two events either way. I can write it as the probability of B conditioned on A, then multiplied by the probability of what I was conditioning on. Or I can write it as the probability of A given B, multiplying that by the probability now I'm conditioning on event B. So both should give me the same answer. And I'll give you a visual of this. I think makes a little more sense here in a second. But I can also rearrange those equations so I can find my conditional probability as long as I know the intersection and the probability of the answer. Well, notice these are things we often have in our contingency table. So even though our contingency table doesn't directly give us conditional probabilities, we can use the components that are in those tables to then calculate that. So before we go to the summary, I want to show you kind of a way to think about this maybe. So let's say I kind of draw a very extreme example. It won't always be like this, but I think this will help with the idea. So I have this entire experimental outcome space area of 1, right? Let's say I want to know, here I've got A, right? So this is my event space A, and maybe the probability that A occurs is 0.1. Try to draw it to be like a tenth of this, right? So that would be what we call our unconditional probability. So what if I wanted to know, okay, what's the probability of A conditional on B? Okay. Let's assume, just for the sake of this example, that here I had event space B. I didn't draw this great, but let's say the area of B, it's everything that's in this entire space. So notice it like completely overlaps with A. I'm using this extreme example to make a point. So let's say the probability of B is 0.2, right? And that, the area that's in A is 0.1. So that would mean like the area that's in B but not in A, this would also be kind of 0.1. Okay. So if I think about it, if I'm conditioning on that B has occurred, what essentially I'm doing is saying, look, I no longer am looking at the entire experimental outcome space, right? So before, when I was looking at the probability of A, I can almost think about this as, well, this was like the probability of A over the entire experimental outcome space, but anything divided by 1 is the same thing. Now, when I've conditioned on B, it's essentially like I'm no longer looking at any of these as possible outcomes. I'm kind of thinking about it as like I'm being told the outcome is somewhere in event B, right? I know event B has occurred. So now I can think about it as instead of like being over 1, my entire experimental outcome space is only 0.2. And of that, how much of it is also, was in event A? Well, it had an area of 0.1. Notice, what does that really look like? Well, this was probability that I was in A and in B, right? That was where these would overlap, divided by the entire area of B, or the probability of B. This is exactly where our multiplication rule comes from. Now notice here, my unconditional probability of A is only 0.1, whereas if I condition on B, well, that means that I know there's a lot of other outcomes that wouldn't be in A that I now know haven't occurred. So it has dramatically changed the probability that I see something happen in event A once I have this additional information. So this is the idea of conditional probabilities, okay? Now in practice, it probably won't be like this, a perfect overlap, but think about maybe, I don't know, another example of how this would look like, how our unconditional and our conditional probabilities could be dramatically different. And maybe I'll show you a case where they'd be exactly the same too, So here's one where it would be exactly the same. So let's say here's my event A, and the probability is 0.5. And then here is event B, also has a probability of 0.5. Excuse me. Well, what if I wanted the probability of A conditional on B now? Well, once again, we could rewrite it as it's the probability of the intersection divided by the probability of whatever we're conditioning on. Or notice, given that B has occurred, I now know I'm only looking at this entire space of 0.5, or the probability of B. Of that remaining 0.5, how much of it is in A? Well, I try to draw this so that like perfectly split the box in half. So if this was 0.5, this box remaining should be 0.25. Notice here, I get a situation where the unconditional, and sorry, I'm writing fast, not the probability of A is 0.5, not the probability of 0.5. The unconditional probability of A is the same as the conditional probability in this case. Right? So you can have this thing occur where you've got your conditional probability and it ends up being the exact same as the unconditional, because of the entire space, A made up 0.5 of it. But once you give me this additional information that B has occurred, well, A makes up half of that remaining space as well. Nothing has changed, right? Having that information essentially doesn't update our probability of event A. Now, another one, once again, this would be where the conditional and unconditional probability aren't the same thing. So if I have, let's do circle A here, and then I had circle B here. Right? If I'm looking actually, well, I'm looking here, the probability of B occurring is relatively large, right? In fact, I'm going to draw this a little bit different just to really make this case. Let's say it was something like this. So the probability of B here, I'll just put a number to it, but I don't know. It's pretty big, right? It's a large portion of this overall experimental outcome space. But if I want the probability of B, given that I know A has occurred, well, now what I'm doing is I'm only looking at this small space of A. I know that I'm somewhere in circle A, and of that, only a small sliver is also in B. So now the probability that I see B occur might be something, I don't know, 0.05, right? It might have been dramatically reduced. So it doesn't just have to be that when you're given additional information, the probability of the event increases. It can also be that it decreases, right? Because B made up a large proportion of the overall possible experimental outcomes, but it makes up a very small proportion of the outcomes that are in event A, which I now know has occurred. Okay? So this might be something like, if I choose a person at random, let me think of a good one. So this would be that once I know that this has occurred. So what, if I choose a person at random, the probability that they are over 6 foot is, I don't know. I don't know the exact numbers, but let's say it's 0.2, something like that. But now if you tell me, well, given that they're male, what's the probability that they're over 6 foot? Well, now I know that has updated quite a bit, right? I know that probability might be very different. Or given that they're female, what's the probability they're over 6 foot? Now I know that probability is probably a lot smaller. So having additional information can allow us to kind of update the probability. And that's because essentially it's like limiting this experimental outcome space we're looking at. Okay. So go back to the slides here. So kind of a summary of our rules. We had that complement rule we talked about in the last video, the addition rule. We now have our multiplication rule. And we can write it two different ways, right? I can write it as I'm looking for the probability of intersection. That's my conditional probability times what I'm conditioning on. Or the one that I think is like more intuitive and kind of matches up with the visual is that if I wanted to find the conditional probability, it's just the intersection of the two events divided by what I'm conditioning on. Okay. And then we can do that either way, right? So I could find the probability of B given A, or I could find the probability of A given B. So, sorry, I got a cat in here today. So what's the probability that given that C2 has occurred, what's the probability R1 occurs? Okay, so now we're going to have to use our multiplication rule. When we're looking at a contingency table, we're not directly given this information. Okay? So I'm going to rewrite this and then think about where those pieces would be in my contingency table. So we said what? We were looking for the probability of R1 given C2. Well, that multiplication rule is that anytime I want a conditional probability, I can write it as the probability or the intersection, probably the intersection of the two events. This is a C, sorry. And then I'm going to divide it by the probability of whatever I'm conditioning on, which here is C2. Okay. So where is this intersection and where is the probability of this event? If we're looking at a contingency table, where's the probability of R1 and C2? That's right here at 0.2. What's the probability that I see C2 occur? Well, that's going to be my total column. So my conditional probability will be the probability that I see R1 and C2, 0.2, divided by the probability C2 occurred, 0.5, or, oops, sorry, 0.2 over 0.5. Okay. So notice the unconditional probability of R1 is 0.6, but the conditional probability, once I know that C2 has occurred, I can kind of think about it as, well, it's not this entire experimental outcome space of 1 now. Once I know C2 has occurred, the remaining area is 0.5. Of that remaining area, 0.2 of it is in R1. So if I know that C2 has occurred, the probability that I see R1, whoops, come on. The probability that I see R1 occur, now just 0.2 over 0.5. Okay. I kind of drew an example earlier, and I didn't mention this term when I did it, but if having this additional piece of information, if the conditional probability is the exact same as the unconditional probability, which was not the case in the last example we looked at, we would say that these events are independent, right? The probability of A occurring is not impacted at all by the fact that B has occurred, okay? Now, I return then to this multiplication rule that has some implications for me. Because now if I want the intersection of two events, if they are independent, well, the probability of B given A, right, that's simply going to be, where is it? There we go. Whoops. The probability of B, right? So I can kind of rewrite this, and here my multiplication rule becomes a little bit easier when those events are independent. Right? Because now the probability I see both event A and event B occur would just be the product of those two. I don't have to worry about finding this conditional probability. Okay. I think here I've got a way we can check to see if they're independent. And I think this example is they are, but we'll see eventually, right? So I can check it two different ways, right? So I can say, are these two events independent? They're independent if the conditional probability of A is the same as the unconditional probability of A. Or I could say they're independent if the conditional probability of B is the same as the unconditional probability. So how can I do this? Well, I can find these conditional probabilities by rewriting them as the intersection divided by what I'm conditioning on. So here, if I want probability of A given B, that's the probability of A and B occurring, 0.15, divided by the probability of whatever I've conditioned on, so B, so 0.15 over 0.25 gives me 0.6. Well, notice the probability of A, if I don't condition on anything, is 0.6. So here, the unconditional and the conditional probability are the same thing. I would say they're independent events. Now, if I had checked it the other way, I could say, okay, look, if they're independent, then the probability of B should be the same as the probability of B given A. So how can I rewrite this? Well, the conditional probability is just the intersection of the two events divided by what I'm conditioning on. So 0.15 divided by the probability of A, so 0.6, 0.15 over 0.6, 0.25. Sure enough, what is the unconditional probability of B? 0.25. So both ways, it doesn't matter which one I use, and I don't have to use both, but I just have to use one of them to prove these are independent events, okay? If they are, I can find the probability of the intersection by taking the probability of A times the probability of B. How can I prove this to myself here? Well, notice, what's the probability of the intersection? We already know it's 0.15, but if I take the probability of A and the probability of B, 0.25 times 0.6, sure enough, I get that 0.15. Now, that won't work when I have an example where they're not independent, right? So here, these were not independent events, right? Because the conditional probability is not the same as the unconditional probability. Oops, let's get that back on the screen. So now notice if I want the probability of the intersection, if I try to take 0.5 minus or times 0.6, that's 0.3. That doesn't give me the right value. So I can only use, where are we at? There we go. I can only use this rule if, in fact, they are independent events. Okay. And I could also, kind of a weird thing that ends up happening is, and yeah, I think intuitively it kind of makes sense, but like if two events are independent, then their complements are independent as well. So this is the idea, like let's say intelligence and height are independent, right? Knowing that someone is over 6 feet tall doesn't tell me anything about whether or not their IQ is over 110. Right? So there, if being over 6 feet tall, right? That's event A, and event B is having above average IQ. Well, those are independent events. Then being under 6 foot tall and not having a below average IQ should be independent, right? Those two things aren't related. So the intersection of the complements, if they're independent events, will also be independent. And so, or sorry, the complements of the two events will also be independent, which means the intersection of the complements should just be the probability of A complement times the probability of B complement. Sure enough, here, probability of B complement is 0.75, probability of A complement is 0.4. 0.4 times 0.75 gives us that 0.3, which was the probability of the intersection of the complements. So just kind of a byproduct of when they're independent events, not only can we find the intersection of the two events pretty easily, we can find the intersection of the complements pretty easily as well using our contingency tables. Okay. Now, what does this look like in practice? So it's kind of you've probably seen it in like in another context, and it just isn't explicitly said, but like think about if I'm rolling a dice, what's the probability that I see 2 3s in a row? Well, the probability I roll a 3 on one is just 1/6, right? 6-sided dice. But if I roll it twice, well, there's a 1/6 chance I get 3 on the first throw, and there's a 1/6 chance I get it on the second. Well, both of these rolls are completely independent, right? The outcome of the first one doesn't impact, let's say I roll the first dice, I get a 3. What's the probability I get a 3 in the next one? Still 1/6, right? It doesn't change it at all. So there, if we want the probability I get a 3 on the first roll, and I get a 3 on the second roll, the probability that I see the first roll be a 3 and the second roll be a 3, the intersection of those two, right? But I got a 3 on the first and a 3 on the second row, just the probability of each one multiplied by each other, right? I don't have to worry about these kind of conditional probabilities. So that's only if they're independent events, right? One way to think, just to kind of, I don't know, I think this is worth, yeah, I'm going to switch desktops here. I think this is what you're seeing now, hopefully. Yeah, there we go. So this is a data set we'll end up working with. But for right now, I'm just going to create another worksheet just to kind of, I don't know, give us a little bit of insight here. So, this idea of independent events gets kind of interesting. I was thinking about this the other day. And just kind of related to something that's happening now. So a huge like booming industry, and whether or not you have interest in sports at all, this is something in the business world you might want to be aware of, is online gambling, right? Like it's on your phone, like you can. So one thing that's kind of interesting is often they try to set these bets so that there's like a 50% chance that it happens, 50% that it doesn't. And the payouts are such that no matter what happens, right, the company's going to make money, right? So you can kind of build like what they call parlays, right? Or you can kind of add in, okay, I'm going to bet that this team wins this game and this other team wins this other game and this other team wins this other game, et cetera, et cetera. So if they're all kind of a probability of winning is around 0.5, well, if they're completely separate games, the outcomes of those games should be independent. So it's kind of interesting, if I think about, what's the probability if let's say I try to bet 10 different games, right? So what's the probability that I get the first game right? Right? Just 0.5. Oops. Well, what's the probability then I get the first game right? Actually, my caps on. And I get the second game right. Well, they're independent events, so it's just going to be, use my equal sign, 0.5 times 0.5. Well, what's the probability I get the first, second, and third game right? Right. Well, now it's going to be their independent, so 0.5 times 0.5 times 0.5. Notice this probability starts to diminish pretty quickly, right? And in fact, anytime you have independent events, you just need to take whatever the probability of the event occurring, one of the events occurring is, and then if it's always the same, like in my kind of betting example, what's the probability that I get 10 games correct? Well, that would just be 0.5 times 0.5 10 times, or 0.5 to the 10th. Notice at 10 games, it's almost impossible. So just kind of a unique application of what we're talking about when we do have independent events. We can kind of think about, really, we're just taking a probability and we could be raising it to a power if it's the same across all of our events. Now, maybe the first game occurring is 0.5 and the probability that I get the second game right, maybe I don't know, took one of their lines that the team wins by 20 runs if it's baseball or something like that. Well, then it would be, 0.5 times, I don't know, maybe 0.05, right? A much smaller probability. So it becomes a little bit, we can't kind of use this power trick. But anyways, so I think that's a pretty good application there. So we'll go back here. We've got our summary. Let me go play from the current slide. So we've got our summary of all the rules that we've talked about. We talked about independence. We talked about being mutually exclusive. Just to kind of round this out, some other interesting examples when we're thinking about independent events. So we know that the probability if I flip a coin that it comes up heads is 0.5. That's the unconditional probability. Over the long run, we know that the number of heads we're going to get is, probably 0.5 or 50%. Over the long run, the number of, if we know that coin flips are independent, right, then, over time, right, as I flip more and more coins, I'm going to see that I get the same likelihood of occurrence. Doesn't matter if I got a heads on the previous flip, the next coin flip should still be a probability of coming up heads of 0.5, right? So this gambler's fallacy question, one thing that we kind of think about is if I have a long run of tails, right? Let's say I get like 10 tails in a row. Will it be more or less likely that I get a heads to come up on that next coin flip? So let's say I have 10 tails in a row. What's the probability that the 11th coin flip is a heads? Well, a lot of people, if we look at betting, behavior, would typically say that they think that a heads is more likely to occur, right? Because we know that it has to even out in the long run. But if they're independent events, it doesn't matter that I got a tails on the previous 10 flips. The probability on that 11th flip is still 0.5. All right, so the answer should be no, but we can kind of prove this to ourselves. So I won't kind of walk through it in Excel, but you can use like a random number generator and then come up with, okay, what's the probability? And here, heads and tails, I just did like heads was 1 and tails was a 0. So I randomly generated a number, either 0 or 1, and did that 10,000 different times. So the probability that every time I saw, the probability that I saw heads right after I saw it come up tails was what, 0.501. So that's my conditional probability, really close to 0.5. Now, because I only did 10,000, it won't be exactly 0.5. Theoretically, I would need an infinite number of coin flips, which we can't really do in practice. But here we get pretty close, right? After I had 2 tails in a row, well, what's the probability it comes up heads? Right around 0.5, a little bit lower here, but once again, 10,000 coin flips. What about if I saw 3 tails in a row? Probably I see a heads now is 0.5. What about 4? 0.5, right? So it doesn't really change it. Okay, oops, there we go. So this is the idea of independent events. So another really good application of this, and has kind of an old story with it, is in casinos, like the roulette table, right? I know there's a green space, but basically you can kind of think about it as like black and red are the only two possible spaces. So if you're betting you land on black or land on red, there's a 50% chance you're right? So there's this casino, I think it was in France. Where do I have it? Did I have? Oh yeah, Monte Carlo. Um, so it came up black 26 times in a row. So kind of imagine like the betting behavior that happened. Now, this wasn't a rigged roulette table. It just happened to come up black 26 times in a row, which is very unlikely, right? In fact, using what we talked about earlier, how unlikely is it? 0.5 to the 26th. I mean, very low, low probability. But once the first 20, once the first, let's say 10 spins were black in a row, what do you think people probably started doing on the 11th? Well, if they fell victim to this gambler's fallacy, like, well, we know it has to, in the long run, the probability would be 0.5. So if it's come up, black 10 times in a row, it's got to come up reds on the 11th time. So everybody put money on red. What happened? The 11th one was black. Okay, well, it's been 11 in a row. It has to be red on the 12th. And they kind of fell victim to this gambler's fallacy. Especially I think I put here by the time it get up to 15. But I mean, you know, people lost tons of money because it just kept coming up black. So you don't want to fall victim to this gambler's fallacy, especially if you are gambling. But we'll talk about it in some other contexts as well, where if they are independent events, we want to be kind of making our decisions like just because we have some additional information, just because we know the previous 25 spins came up black, the probability if it's, if they're independent events, the probability that the 26th spin is black is still 0.5. Okay. And then we'll do an Excel example, kind of looking at all of these different rules, how we build these contingency tables. So up to this point, I've just given you the numbers, but we use the empirical probability assignment method quite often to build our own contingency tables. So I put here, I've got a union membership wage differentials example. I might put two examples up there, but I think the one that we'll probably look at, I got some newer data that I think is interesting is like some COVID data. So we'll probably take a look at that. And if we have time, I'll do an additional example in that Excel video as well. But that will be what comes after this.